that. So it's dark enough. It's cloudy. I can get off my shades. I think I'll wear them anyway. It's bright. So I'm waiting for the pharmacy to open. I need some antibiotics. I cut my foot really good yesterday. Real, just kind of a fluke. I went to move my foot and I brushed past a bag of trash. I bagged up. And I don't know if I kind of stumbled or just went to step my foot down to pick it up, reach over and pick it up. And I ran my foot across it, and a can lid, like you use a can opener, take a lid off a can, was in there, and it sliced my foot right open. Just, oh, nasty little gash. And I, put pressure on it, bandaged up, and I thought it was getting better. Cleaned it. And then a few hours later, it was throbbing. It was real sore. It was hurting real bad. And it was fine at first, and my shoulder was beeping at me, so I had to get up and I walked across the outside and back around, and I guess I stepped just right and pulled it back open, right? It was sealed it, pulled it back open a little bit, and it was just enough that a few hours later it was still bleeding. So I went ahead and drove into the hospital, and had them clean it. Oh my god, it was just unbelievable how bad it hurt. They're sitting there scrubbing the wound, just hurt like the dickens. Unbelievable. So we went ahead and got that cleaned up and taken care of, and then they put some betadine on and everything. They put a little, they call it Dermabond. It's super glue. Cleaned it up, but put in a little splint so it wouldn't wiggle. And then instead of driving all the way home and back around, I pulled over at camp. I've got a video I just uploaded earlier, Rising Green, a little short there, and that's at one of the little conservation areas I tucked into and caught a few hours of shut eye. That way I go over here. I go to the pharmacy over here at the big box store, and they're closed until 9. So I got an hour. And so, welcome to chat. I thought I would spend this hour. We're going to discuss some advanced computing platforms. And part of why I do this is to help me establish prior art. I can get this information out there. So if you follow the channel at all, I work on all kinds of technology. I consult on things. Somebody asked me the other day, and I was like, no, I've consulted on a satellite for the ESA, European Space Agency. I have an online friend. Um, we'll just call her Dr. Sarah because I don't want to dox her, but Dr. Sarah did some work for a company, did some work in the space. And she's a wonderful mathematician. She's a brilliant mathematician, but she's not that experienced in electronics. And so she gives me a call, and I had to look, it's friendly consult. It's not anything I'm going to put my name on, but I did consult on a satellite on relative voltage planes. They had a 5 volt and 112 volt or 7 volt or something. And I was explaining that you can get that out of having multiple voltage planes. So you set one voltage here, and you got your high voltage here, and then you got another one real close. So the difference between this and this is one thing, and the difference between this and this is another. The difference between here and here gives you a third voltage plane. So you have all these different voltage planes you can use relative ground. And when you're on something like a satellite or a boat where you're not connected to the ground, that's actually how you do it. So airplanes, that kind of stuff, weather balloons. So relative ground planes. And I've worked on platforms for nuclear reactors. Everybody knows I've got some micro reactor projects I'm working on. Now they're on paper. We're just doing the basics on them. But one of the things we get into here at Wayfarer Technologies is advanced computing platforms. And I've talked a little bit about in-memory and near-memory computing. And so most of our computers today are von Neumann or Princeton architecture rather than Harvard architecture. That means you've got code on one side and instructions on the other. You got data and instructions in two different places, and they come together at the CPU and they get processed and dealt with. Unlike a Harvard architecture where those are interleaved, they're kind of together, and so they're stored. The operation you're going to do on the data is right next to it. It's together in the place. Instead of having the cookbook and the ingredients over here, you've got a bunch of ingredients with sticky notes on it that say what to do with them. A little different. So miss in place. Okay. So that's very briefly, but basically the big difference between the two platforms is in Harvard architecture, you have your instructions with your data, and in von Neumann or Princeton architecture, you have data in one place and code in the other. They get worked. They come on different pipelines. or different address ranges. That's not to say they're stored on the hard drive, but in memory while the program's working. They're kept in different areas. And there's advantages to both. Most computers you use today, Windows, Linux, all that, x86, the architecture, it's the physical chip. So x86, x64, Pentiums, right? They use von Neumann. And then you have a few microcontrollers. I think there's a couple of, I think the PIC, PIC 18, 16, 24, the PIC architecture, they use that Harvard architecture, or often do. And things are brought in and then split near the chip. So in memory and near memory computing, in memory means your RAM, you're going to have a little processor on or in each RAM chip as part of it. And you do them because the biggest use of electricity, people talk about the data centers and all the electricity that gets used. A large portion of that is to take information, data, out of memory or the hard drive, take it to the processor, do the computation on it, and put it back in memory or on the hard drive. And if you can have a little tiny processor on each stick of RAM that can do the basics, you eliminate a lot of that movement, a lot of that speed. The alternative would be to have a huge chunk of cache, and it's really expensive to do. Okay, so it's a trade-off. So we may change the way we build computers down the road. Quantum computing is its own thing, and I'm of the opinion that quantum computing is closer to a Harvard architecture than anything. The technology is still way too new. It's way too new. So one of the things I want to talk about today is some projects we're doing at Wayfarer. We love the 6502. We love the 65816. We love the 65XX series of processors of computers. They were developed back in the 70s by Bill Mensch and Chuck Peddle. Chuck Peddle has passed away. Bill Mensch is still kicking. They run Western Design Center, one of the first, I think it was the first, fabless computer design company. So they design chips without actually making them, and they license the technology out to other foundries that make chips. And so you'll find these in all kinds of stuff. The 6502 was used in a slew of computers, the Acorn, the Atom, the BBC Micro, the Commodore 64, a bunch of those old early 80s, late 70s computers. They used 6502. And then they developed on top of that. The Apple, one of the Apples, the early Apples, the 2E, I believe, was 6502. And the 65816, if I remember correctly, was used in the Apple II GS. So they use them in pacemakers. They use them in microcontrollers. And ST Micro, I think it's the ST7, ST8, same thing. They are so similar. They're almost identical. So the 6502 gets rebranded and used. It was used, the Nintendo Entertainment System, the chip in it was a modified 6502. They pulled off binary coded decimal and added a couple of odds and ends. So, but it's the same chip. It's the same assembly. So an assembly language is, of course, your machine language, and it's different for each kind of microchip you have. So one of the things about the 6502, it's an old 70s chip, and so it doesn't have all of the same features as modern computers do, modern CPUs. And one of the things that was never really developed for it was a math coprocessor or floating point unit. And so if you go back in the day, we're going to talk a little bit about the difference between fixed point and floating point computers. So a fixed point computer is great for something like money, okay? You always have a decimal point. In America, we use US dollars at this point. Basic currency. We'll get into fancy stuff in a minute. Basic currency. You have dollars that can be very big, anywhere from 0, 1, 5, 10, $773 billion or whatever, right? GDP, 2.4 trillion, whatever that big number is, the dollars. And then you have cents, per cent, per 100. And so you have two decimal places. And so that decimal point is fixed. Blah, 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 blah this way. Dot, 1, 2, tenths, hundredths. Okay. And you get into accounting, you might get into fractional cents, smaller amounts. That's okay. The nice thing about this is you can record it as dollars with the decimal point or cents and move your decimal point over. Okay. But that's a fixed point system. Another example might be your thermostat in your house may only have tenths of degrees or degrees. Okay. It's going to have and show you the temperature at 67.3, 67.5. Speedometers, odometers, they're going to have a fixed point on that odometer. It only reads you 1/10 of a mile. It's got one decimal place. And you might have something else where the fixed point is many decimal places over. Okay. So fixed point gives you a fixed position for your decimal point and a set number of numbers on either side. Okay. So what that lets you do is know where that's going to be. Now, floating point is different because if let's talk for a second here about orders of magnitude in engineering or scientific stuff. So if you're working on biology, you need one range of numbers. You need them to be small, millimeters, nanometers, right? If you're working in atomics, you need femtometers. Pico, you're at that femtometer scales, right? Little itty bitty tiny stuff, angstroms. You need many decimal points to the right. And if you're in cosmic stuff, if you're doing astronomy and you're trying to measure the motion of planets or galaxies, you might not care about femtometers. You're worried about big giant parsecs and stuff. You're worried about big giant measurements, billions of kilometers, right? Okay. So these are different scales, and so you need different amounts, and so that point has to float. It has to move to different positions. Some basics of fixed point versus floating point. Okay. Right. So one of the problems we have is how do we represent this? So I'll give you an example here. In decimal, we can only go to the tenths, and then we have to go another decimal place to add another hundreds, thousands, 10,000s to go to another order of magnitude. We have to go and add a space. In a computer, clearly we have a limited amount of space, but we're also in binary. So each time we move over, we only cut it in halves, quarters, eighths, sixteenths, 30 seconds, 64ths, and then 1/28ths. So we've got all these decimal points over. Now we can represent two decimal places, hundredths. Okay, right? You with me? Okay, so the bigger we go, you need, what is it, like 11 decimal place to get to thousandths? And so it's like 3 of these or whatever per point, three something. It's a shift that you have to keep cutting these things down. And you also run into, what if I need to represent, if I need to represent 0.5, I can do that with 1 bit. That's half. But 1/3, what's an accurate representation of 1/3? Because if I've got 2 decimal points, I can get to quarters, 25, 50, 75. Okay, right? Okay, and then we go 1.25, and then 0.670, and it gets smaller, but it's not decimal numbers. And so there's a rounding error when we go from one base of base 2 to base 10. There's a big problem with that. So that's what floating point units do. And I believe it's IEEE 754. That's IEEE, the International Electronic Engineers and Electrical IEEE. They do all this stuff. They set a standard 754 that says floating point numbers are going to work like this. And the reason why, if you go back to the early 70s, early computers, you have the PDP series, PDP 8, PDP 10, PDP 11, the VAX, the IBM System 360, all of this different stuff use different formats for storing those floating points. And so you have, basically you've got a number, and then you have an exponent, okay, and then you have a sign bit. But you also have a signed exponent and a signed mantissa or significand, and you have different sizes of significance and different sizes of exponents that let you represent different ranges. And so the big one today is 64-bit floats, and it's 52 significant, 11 exponent, and 1 sign bit. positive or negative. And the reason we use 11 sign bits is because it gives you an exponent in the plus or minus 1,000 range. They're all offset by a bias, right? So you can get any number, a sign bit. And some of them have multiple sign bits for both parts of the number. Think about scientific notation. You have a number, and it might be a decimal number with a bunch of digits times 10 to the whatever power, 10 to the 20th, 10 to the third, 10 to the minus 15th, whatever power. That's scientific notation. And that's a floating point number because by changing the exponent, we have a number, right? It's usually got a leading number. It's got this other number that comes after it. And then we multiply that times 10 to a certain value, and that moves the decimal point based on the exponent value. You with me? All right. So there were all these different computers back in the 70s, and they all used different floating point representation. And because of this, things were hard to translate programs and translate data from one to the other. We had a terrible, expensive loss on Mars some years back. They had sent a satellite over to go, a rover or something, and they went to shift from meters to kilometers to miles, or meters to feet or something, meters to yards, and they didn't correct for it properly. And the translation was done. And so this thing smashes into Mars at highs and just blamos right into it. Okay, I think it was miles per hour to kilometers per hour, something like that. And just smashed it off because they didn't do the conversion correctly. It was just off by enough. And so this, ruined $1 billion project because somebody didn't check what they were doing. All right. So that caused problems in computing. So the IEEE comes out and makes their standard and says it's all going to be this way. And you have different sizes. There's half and double and long and all this different kinds of floats to give you different numbers. So the 6502 has no way to do this unless you do it in software, and it takes a long time. So a fast floating point unit is a desirable thing. There's also no multiplier divide circuits in there. There's a lot of stuff that's not in the 6502. What it does have is all 16 of the base binary operations that can be done in Boolean logic and allow them to function as such. Those are the ALU, the arithmetic logic unit. And on a careful examination of the 6502 and the way its registers are set up. Hello, Zorro. How are you? We're discussing computer architectures. So as if you look at different kinds of them, you got 6502. I'll cover a few. 6502, the MIPS, okay, and the x86. So an x86, we're x64 now, 64-bit x86, x86 64, same thing, Pentiums. They have one architecture, and they were designed to be very much like Granddaddy PDP-11, big old mainframe thing, do everything. So there's a lot of special purpose register. Put a number in this register and put another number in this register, and it automatically puts the product, the multiplication of those two numbers in this other register. This register is always 0. If you put a number in this register and a number in this register, it'll swap the two of them. You hit a command and just flip them both. It'll swap them. Bunch of special purpose registers. And a register is a set of bits. So you take something from memory, you put a byte or 16 bits or 32 bits or whatever, and you put them in this register, this special spot, and it'll do stuff with the numbers. x86 is filled with those. And we cannot play music on here. I apologize. I would, but they don't like, YouTube's real big on copyright, so I just don't have it. I'm not set up to play music on here. So to chat there. So the MIPS is a little different. It's got like 32 special registers, and some of them are special, and one of them 0. It's always 0 no matter what. A couple other things. But they're more general purpose. It's very streamlined. There's only a certain number of instructions. MIPS architecture is very streamlined. And then I am from the USA. I am for chat there. I am from the United States of America. Um, and then 6502 is it's really built on that Motorola stack, and you go back to basic Boolean algebra, and uh, you've got 16 Boolean operations that kind of define Turing completeness. And so if something there you can recreate many of those single gate theory, but these are the basic operations that you want to be able to done, and most computers have these operations. Well, the 6502, it's only got 5 registers, not 32, not dozens. Okay, 5 registers plus a clock. And so a lot of its instructions are just loading things to or from those, storing and loading things to those registers, and then those 16 operations performed on it. It's a very streamlined architecture, but it's missing a lot of stuff: multiplying, dividing, doing floating point operations, a lot of things that are taken for granted now. And so that kind of gets us into, now that we've spent 20 minutes talking about computers, we're going to talk a little bit about one of the chips we're working on for the 6502. So everybody strap in. We're going to go down the rabbit hole now. So we've discussed that one of the problems we have is having or not having floating point units and how to represent floating point units. There's somebody over here doing something. Oh, they're picking somebody up over here. They just honked. I was wondering why they're stopped and honked. That's what I get for sitting in the parking lot. There's a little distraction there. So, how do you represent these numbers? What are some numbers you can represent or not represent based on, right, these things? How do you represent ratios like trigonometry, cosines, the number pi, irrational numbers, phi? And phi is a really interesting one because there's a way you can represent any integer number with a base of phi. So you got bases of numbers. Base 2 is binary, base 10 is decimal, etc. We can also have base phi. And base phi is interesting because you can use a balance of exponential multiplicands of phi to get to any integer. Anything can be described by phi or powers of phi. So that's one of the things that we're looking at there, is using finary or finery. But we're looking at a specialized processor, a coprocessor, to go with the 6502 to add a series of operations, whether it is the fixed point numbers we talked about, which are going to be very helpful for some people. We may have that be um, modifiable by where your fixed point is. We may be able to set a fixed point and then do operations on those fixed points. We're not sure yet exactly how we want to do that, or if we're just going to use 8 on one side, 8 on the other. We really do like the 11 point exponent because 11 bits in binary gives you 2048, 2048 combinations. And if you split that in the middle, you can go to negative 1023 and positive 1024, including 0. And that gives you 1,000 units below and 1,000 units above 0, 1,000 negative units, 1,000 positive units. And so then you have the ability to, you've got 1,000 delimitations. You can go to 1,000 that way. And for an exponent, that's 1,000 decimal places or what have you. Okay, 1,000 points. And again, as we've discussed, when you turn that back into binary, or from binary to decimal, you lose some loss. We've got quite a bit of range there that you can use to now take a large number and move that digit around. So we really like the idea of that. We are considering 32-bit or possibly higher for our significand. And the reason why is that will allow us to work with 32-bit numbers as integers. We can use the same hardware on it. And then we just have special circuitry for our exponents. And that'll give us some advantages there. So when we look at a fixed point, we may also want to use these same numbers in there. Now at 11 and 32, we're only at 43, right? So that leaves us 5 bits left that we can work with for special numbers. And so we want one for sign. We may want one for to tell the computer whether or not this is a rational or irrational number, whether or not this decimal repeats. Because there's a lot of irrational numbers. There's a lot of repeating decimals out there, right? So when you get into things like cosines and phi and pi and whatnot, you have got all of these different things set up so that the number just goes on and on and on forever. So when you start doing floating point operations, it's easy to see where that's going to have errors. You're going to have run into a limit. And so just telling the computer, hey, this number is a ratio of a fraction. It's a rational number. And it does break down to something. It repeats. It looks like at 1/3, it's going to be threes all along. And so you can do, some math on that, or at least tell the computer to expect it. And you can have some special circuitry or special routines to correct for that. So let's consider if you've got 030303, 33333 or whatever, and you've got this running. Well, how do you determine, when you stop, and when you do stop, do you round or truncate? And what do you do with that if you add two of these together? Right? Okay, do you just get 0.666 and know it repeats? Do you know it repeats, or does it stop? What if you add that to 2/3? Okay, so now we can say that 0.333 repeating and 0.66666 repeating is not 0.99999. We know those repeat forever, and when added together, it will equal 1. 1/3 plus 2/3 is full. And we can represent this way. A rational number, right? Okay, so that's one of the things we're looking at doing. Can we have these rational numbers, fractional numbers, and how do we represent them so that there is a more correct representation? Right? So we may do some fixed point math on that. Now you can get some strange ratios, but how many digits do we want to have for that numerator denominator? What's our limit? What's our range there? Do we want to worry about fractions that are smaller than 32,000? Right. So how big are these numbers? And fixed point math gives us an opportunity to do this. We can have a number of each, and then when they add up to the same, we know they're there. We can do some reduction operations on there too. We can make these things simple, especially if they're divisible by 2 or powers of 2. So, or other things that we can represent and convert between bases. So something's divisible by 5, we can shift that and say it's divisible by 0.5. Now it's a half. We can do that evenly. We can do that squarely. So that's some of the circuitry we'll be looking at there. And we may use a multiple fixed point representation on this, Q numbers. Those are called Q numbers. And we may do some floating point operations. We would like to be able to tell the computer if it's an irrational number, if it's a repeating decimal. Is it irrational and does it repeat? Those are two things. So rational, irrational, does it repeat? All integers are rational. It's that number over 1. Okay. And a number over 2 or a number over 4 are rational numbers. They'll evenly divide. Well, generally. But what if they're not? What if they're irrational? And how do we represent those ratios? How do we represent fractions on a computer that makes sense? So this is some of the stuff we're looking at doing. Again, we want to use some fast multipliers, fast dividers. There's some algorithms for this. And another thing we're looking at is using symbolized math. So a lot of times when you put in a number like the square root of 5, which is useful for determining phi, the golden ratio, that number is stored as a binary string. Well, we want to be able to store it as a square root. We want to know that that's a square root and tokenize it as a square root and be able to do operations with square roots, radicals, numbers, right? And a square root is just a negative radical, right? A root is just a radical. It's of a negative number. Square root, cube root, right? Pentaroot, whatever. So we want to be able to store these things in these ways and be able to use them while they're still in that symbolic form before it's expanded to a big string of numbers. And by doing so, we will help eliminate some of the floating point errors. We'll have more accurate mathematics. That's a big jump for little tiny processors. So some of the things we're trying to do there, logic, there's Prolog has a thing called a Warren abstract machine. And we really want to look at maybe going to the 65816 for this because it had a relocatable stack. I believe the 65CE, CMOS Extended, which was done by the CSG group way back in the day, and it's long abandoned. It is gone, gone, gone. Those patents have long been lost to the internet, and recreating its functionality is almost trivial at this point. So we're going to do some things similar to that. We're going to base some things on that when we use ours because it will give us a relocatable stack, and that will allow us to have multiple stacks defined and then jump and move between them, our index to our stack. You have certain operations on the stack. You push things on top of this. It's like a stack of plates. You ever work in a restaurant, you got a stack of plates, you put a plate on, it pushes the stack down, you pull a plate off, and the whole stack lifts up. There's a spring on the bottom. That's how stack works. You push things on the top and pull them off. The last one on is the first one out. Last in, first out stack. So we're going to be doing something with that because Warren abstract machines, which are used in Prolog, it's a language, they allow for constraint-based programming and predicate logic. And so when you start getting into algebraic systems, like if there's a number in the numerator and the denominator, they cancel out. We want to be able to do that logically before we ever put a number in there. We just want to know that X goes away a variable. We want to know that, right? That kind of thing. So being able to have a lot of variables to find, just one byte, and know that that's a variable, and then have a key for it, we can tokenize these, right? X, Y, Z, whatever letter. And we can tokenize these, and we can work on them with symbolic math. It's little things like knowing algorithms on how to do the FOIL method, first, outer, inner, last, to solve binomials, things like that. Yeah, negative b plus or minus the square root, quadratic formula, that stuff. And so, just a quick email there. We want to be able to work with symbols, not numbers. We want to work with variables. We want to work with square roots. We want to work with radicals so that we can perform algebra operations on them before it turns into a number, and then we're doing arithmetic. Because again, a computer is limited and it represents numbers differently than we're used to. And when we convert those numbers, we kind of run into some stuff, right? I mean, there's some stuff called binary coded decimal, and it's its own thing. There's some circuitry for it, and you'll always get a decimal number. But people don't use it anymore. Okay, it's inefficient in its own way. So it's like this: in a byte, 8 bits, you can store 256 values. In binary coded decimal, you can only store 100, 0 to 99. So you lose more than half your precision, half your storage there, your efficiency, for a trade-off to have a decimal number. It has its advantages. You don't have to convert bases, and your floating point numbers are all different. If you're doing accounting, people really like it because it's the same number on paper as it is in the computer. There's no shift. So we're going to look at whether or not to use some BCD, binary coded decimal, or not. I don't think we're going to. It may be. It just depends. If we take the binary coded decimal stuff off and remove that mode from our custom CO2, we get an entirely different architecture. A lot more spaces, a lot of instructions we can reuse. So fixed point numbers, floating point numbers, and symbolic math. Those are some of the things we're looking at. A computer algebraic system and a way to define our numbers that goes beyond IEEE. So maybe finary, some way to represent this number. Spigot algorithms. A spigot algorithm is neat. So when you compute something like pi or phi, you usually start at the left and you work your way to the right and you keep doing stuff and pull the remainder down and do the next part of the division, pull the remainder down and do the next part of the division, and you keep carrying around and doing this math on it. You keep going. A spigot algorithm says we don't need anything. We can start at 1,000. We can start at 1 million. By doing this math this way, we can know exactly where we're going to start and we can spit out a number from there. So you can start at the billionth digit of pi. You don't need to know the 999 millionth, 999,000th, 999th digit of pi. You can just start at 1 billion. The spigot algorithm works like a faucet and it spits these out. And they're pretty neat. They're pretty neat little things. Um, you may need to know that one, but you don't need to. You may need to know the 999th, but you don't need to know 998. You just have to have one to give you a place to start, so you can stop and step on, and that's really handy for us um, for helping with our accuracy and for working with really big numbers. We will then only be limited to precision by what the computer has in memory and storage space or what's defined by the programmer. So that is a tremendous advantage we're looking at there, is using hardware spigot algorithms. I believe it's the BBP or BBF, BPF, one of those. It's an algorithm for computing pi, and it spits out digits of pi. So we have a tremendous advantage right there that we're looking at, to be able to go in and say at the hardware level, we don't have pi stored to this many digits. We just have a way to make pi to any number of digits at any level of accuracy. And I think that will be helpful for us. I mean, we're only working on an 8-bit computer, so 16-bit computer at this point, but there are designs out there that extend these to those higher bit widths, to these higher register sizes. Let's talk about 8-bit and 16-bit computers, 32-bit computers. We're talking about how big the registers are. We talked about registers earlier. They're a special place to store information. So, what are we working on? Again, fixed point units, Q numbers, floating point units, fast multipliers and dividers, symbolic math and constraint based programming, and spigot algorithm hardware for some of the transcendental, the big numbers like pi and phi and Euler's number, square root of 2, square root of 5. Square root of 5 is really a big one for us. So we want to make sure that we have a way to work with these numbers at really large levels. So that's some of the stuff we're working on here at Wayfarer Technologies. And again, we want to be able to um, tell this chip what we're sending it or what information to go get on its own, and give it a memory address and say, hey, go get the memory addresses here and here that are this size, these indexes, this many bytes. Go work on them and do this work. We may have some internal cache or storage for it. We're really thinking about maybe putting in 127 bytes or 256 bytes of information. I would say maybe even having on cache, rather than registers, just having a little bit of internal working RAM, special registers, um, so that we can send it an instruction with its internal information. Okay, they can work on it. So do this operation with this number and this other number. the minimum number of instructions we need to send the coprocessor and get the answers back, and then read it, have it put into another address. So there'll be, it will have a dedicated link of addresses that go straight to the 6502, the CPU, and then it will probably have its own data bus to go get information from other places. It'll have some locking. It'll have some DMA type stuff. We got a DMA controller we're working on called the Isaac, the ISA controller. We're going back to the ISA bus. The reason why is so many things used it and it's well defined. And there's some other standards. Laptop cards, PCMCIA, people don't use them much anymore, but PCMCIA is based on this ISA bus. So is several other things. So we're going to be going back to this architecture and using it for our purposes, so that we've got these DMA controllers. We've got old 8-bit and 16-bit peripheral cards. Be very advantageous to people. So we're working on this memory controller, this DMA controller for our system. And then at the same time, we want to have a coprocessor in there so that we can do some things with it. So that's some of the stuff we're working on here at Wayfarer Technologies, is these different architectures. Isaac, and we haven't named our math chip yet. I was going to maybe do the 6517. I don't think 6517 is used yet as a number. Q is the 17th number or letter in the US alphabet, English alphabet. And so that Q, it's kind of Q numbers, fixed point numbers for those kind of operations. Quotient, able to do rational numbers, able to do quotients. So that's definitely a thought there, is to have the 65 or something, but we need to name it. We got to name it something. So math assistant chip, Mac, Isaac and Mac. I don't know. We haven't decided yet. Somewhere in there. All right, so that's 45 minutes there. We're kind of getting to a lecture on the different architectures we're working on. I genuinely think this will be helpful for some people that want to do very complicated scientific math. At the end of the day, it's a fancy calculator. It's got this little chip in it. It's going to do some fancy calculator stuff. We do, however, look at the 6502 as a core architecture that can be extended. And extending that, 65816 took it to 16, 658/16, because it's 8 or 16 bit. Going to the 832 or an 864, the 6564, 64-bit 6502. And where we get in that is we want to look at doing multi-core processing. So 8-bit cores that can hold hands and chain together to be a 64-bit chip. And we really like the idea of being able to do something with that. We have a 6404, which is a 4-bit microslice processor that can be chained similarly to perform some fast matrix operations. We had some things that came from there doing matrix stuff, whether it is row shifts or column shifts, or the ability to transpose matrices. Now, in this one, we were just looking at doing numbers that were 1 bit, to do zero matrices of zeros and ones. But if you use a grid of those together, you can now do hexadecimal operations using these 4-bit registers. 4 bits holds the hex key. So with 8-bit, we now have 8 of these. We would definitely consider going to 2 of them, which would allow dual 64-bit processors that each have 8 cores, 8-bit cores that work together in a dual processor environment. And now we can work on some really big numbers, work on 16 numbers. We may even go to a higher, we may go to 16 cores, 16 8-bit cores, or 16 16-bit cores, which gives you some really big numbers to work with, some really interesting numbers. And so those are some of the things we're trying to do there, is to be able to work with these symbols Warren Abstract Machines, which lets you do callback and traces on stacks for pattern matching, and that's where you get your predicate logic and your tokenization. Um, right. So that's what we're working on here. I'm going to go ahead and call it. I've been on here for 45 minutes. I've been talking nonstop. And those are the architectures we're working on. I do think that taking the 6502, it's got a really comfortable architecture. It's easy to work with. I also really like MIPS. I like the way MIPS works. It's real clean. It's real pretty. MIPS was used in the PlayStation. So I think it was an R3000 was used in the PlayStation. Or an R4000 was. I think R3000, R4000, one of those also became the Emotion Engine. It was a MIPS. 32-bit registers. Real nice little system. Only a couple of special purpose. The 6502 really has a lot of advantages. It's got a lot going for it. It's a nice little engine that could, and it still does. They use them in pacemakers. 6502, the Nintendo, is in pacemakers. It keeps people's hearts beating. So I think that's really neat. I don't remember if it's in insulin pumps or not. It's one of the only chips that's automatically approved for use in the human body. It allows that because it's so well understood. Even its undefined behavior is now incredibly well understood because people went in and just saw what it would do in a variety of cases. So extending that platform, modifying that platform so it's still got this familiar architecture that's used in microcontrollers and coming back around with it full circle to do other things, I think is of a tremendous advantage. And developing these math coroutines and these math processing routines is really helpful. It's all based on the Motorola. Um, my phone's a Motorola. Use a lot of stuff. The Motorola stacked MC 14500B. Now that's an interesting little chip there. And I talked a little bit about Turing completeness. So the MC 14500B was a 1-bit computer. It could only operate on 1 bit at a time, but it could do all 16 operations, load and store. And so it had, it could only compare to what's in memory. It's 1 bit of memory to one space at a time. But you can run a factory with that. It was used as a control system to replace boards of relays and could run entire factories on a 1-bit computer. Amazing, a 1-bit computer. If you just need to know if a sensor's been triggered, yes or no, something's on or off, yes or no, what do you need more than 1 bit for? So that same Turing completeness, that same stack, I really feel was extended into the 6800, which the 6502 was based on. It kind of comes down to the ALU and some of the operations you can do in binary on Boolean algebra, binary algebra, Boolean algebra. And that's why a lot of things work the way they do. The stuff they've learned to do with these operations is just amazing. A lot of these are the ones that Alan Turing said, this is what you have to be able to do anything. And I think that there's more. I think there's more out there that can be done. I think there's a lot of logic operations that are not done or that are compound operations you can put together into a single circuit. Part of it comes down to you can only do so much with a switch and a group of switches in order or combinations. So these go back to relays, how relays worked back in the day off the trails. So it kind of comes down to electrical theory. And as we move into more advanced architectures, as we move into different architectures, as we move into different technologies, different geometries of our silicon, different compounds applied to that silicon, we're going to get different operations that become available. They may become emergent. But everybody's kind of stuck in do this and make it faster. Do this one thing, make it faster. Do this one thing, and this is done a lot, so let's make a special circus that does this one thing a lot faster, better. less steps. And that's important to computing in general. But as we move forward, as we look at different things, it's important to branch out and reach out. And one of the problems we are really big on solving is how do you identify and how do you represent and work with numbers like phi, numbers like the square root of 2, numbers like the square root of 5? How do you work with these numbers that just go on and on forever? What do you do with them? How do you deal with them? So we have some ideas and some things, and I'll talk about those in a later video. I'm getting ready to go in the store here. But we definitely want to look at what we can do with these numbers, how we can represent them as a symbol, x equals the square root of 5. Well, let me give you a quick example here, right quick, and you can try this on your computer if you happen to catch this later. If you go to a computer, and in most programming languages, you put in 0.15 plus 0.15, and you make that equal to a. So you take a variable and you assign it to 0.15 plus 0.15. And then you take and you put in 0.1 plus 0.2 is b. And you say, does a equal b? It'll tell you no. Because one of them is 0.30000, and the other one is 0.300000004. Floating point error. Okay. It's just how it works. So on a computer, even small, simple numbers that you would think both equal 0.3 don't. And so, how do we represent these things symbolically? How do we represent these things in a way that's not going to mess up? And how do we do it efficiently without using a ton of extra space, a ton of extra RAM? Can that be done? Can we do this without using up tons of space? And when you get into big numbers and big data sets, it really does matter. But what can we do with it? What can we do here to go back to a smaller, simpler architecture, time gone by, and go back to that branch and go off in a different direction and focus on these different things? And I think that that's an important thing to do. So that's part of what we do is Wayfarer Technologies. We explore the horizons that have not been looked at yet. We go off on the trail less traveled, off the beaten path, and we see what we can find. We see if there's useful things there. And you know what? Sometimes we find amazing views. We find beautiful, amazing views. So, like I said, this is just a discussion of some different computer architectures that's there, that's available. Some of the stuff going on. This is just a different view of how to work with numbers in a way that's going to let us do math that's more accurate, that's more symbolic. You know, you got to do a lot of work to make something that solves algebra on a computer. And there's some algorithms out there that do some things very eloquently. But some of those eloquent algorithms break down, those ways of solving math problems break down when you convert a number into binary and try and store it that way. So we're looking at ways to store those numbers differently, to store them better, to have more accuracy and more use of them in the long run. So I just wanted to take a little time here today. I've got an hour to kill. I'm going to go in the store. I got to the pharmacy, get some antibiotics. I cut my foot open really good last night on a can lid, and I had a little bit of time to kill. So I just want to stop before I go get coffee. I've got a great little parking place. I'm right by the door of the store here. I didn't want to lose it. So we're coming up on an hour. But yeah, I just want to take some time to talk about some of these things. Spigot algorithms, Warren abstract machines, symbolic math, computer algebraic solvers, fixed versus floating point numbers. That's kind of the discussion for today. And how do we represent these things? What do we do with them? So that's what we're doing, is looking at building different circuitry for the 6502. Or, you know, you can interface with this thing with any processor, but to keep it simple and work with numbers the way we want to work with them, to use the bits the way we want to use these bits. So thank you all to everybody that stopped in. I'm going to go ahead and kill chat. I'm going to go in the store and get my prescription for my antibiotics so my foot doesn't get infected and I don't have to have a toe amputated, because I about amputated my toe. Oh my God. Caught it just right. Thing just would not quit bleeding. Got it just right. Just would not quit bleeding. So, owie. But I went to the doctor and had him clean it. It hurt more for him to clean it than it did to cut it. I tell you what, kept scrubbing the thing. Oh, the nurse with the brutal bedside brutal gentleness. No, it is not gentle brutalness. Not gentleness on my foot. She brutally cleaned that wound. So, all right. I'll see you, chat. I'll see you, YouTube. It's good to see everybody. There's not a lot of people in here today. I didn't think you'd all want to listen to me ramble on about computers, but I was killing time, and I'm glad to have done it.